So thanks everybody for joining, and thanks Allison and other team leads for inviting me to speak here. I'm going to talk about MOSAIC, and I'm going to provide some an overview, especially kind of focused on the observations, as Wisla will talk more about some modeling activities. And I know that many of you have probably seen some of this presentation before, including those that last week were at NCAR. You've seen most of these slides. Anyhow, I'll get right into it. And really the target here is enhancing our process understanding of the coupled Arctic system using MOSAIC. And I speak on behalf of many. There are literally hundreds of people involved in this across the country and across the world. So it's a very large consortium involved in the planning for this activity. Oh, there we go. Sorry, my advancement was not working. Okay, so a little bit on motivation. I really stripped out most of the motivation because I believe we all get it largely. Largely we're motivated by Arctic change. So the declining sea ice, Arctic amplification, some of these large-scale processes, but more importantly for MOSAIC, we're motivated by the process level changes, the details of the system that are important. So as the sea ice thins, how does that impact energy transfer in the system? How does that impact how that ice changes over time, how it cracks, etc. The relationship to larger scale circulation changes in our global system, and of course biogeochemical cycles, etc. So there's a lot of process level changes that are happening as well that are really important for us to understand. And of course the implications of those changes, I think we all understand that in terms of the economics, resource development, ecosystems, the connection with lower latitude weather, things like that. So there's a lot of implications, and so I'm not going to belabor the point on the motivation here, but more move towards some of the more details of the project. We do recognize, though, and ultimately the kind of foundation for MOSAIC has been built upon the need to improve models. And models are here loosely described across three different realms, so weather scale models, climate scale models, and sea ice forecasting models. And the thread that ties these all together is ultimately that each requires on representations of the system. In this case, kind of the physical system, but also the chemistry in the system, the biology in the system, et cetera. So we really have to understand the processes. And the IPCC over the last number of years has pointed to some of the major deficiencies that we have in our ability to represent the Arctic system and its changes, especially with relation to things like sea ice forecasting and prediction. And some of those deficiencies include things like clouds, boundary layer structure, in both the atmosphere and the ocean, winds, surface fluxes, ocean mixing, and ultimately a lot of these deficiencies are based on a lack of observational data, especially kind of data that are well positioned for those processes and the coupling in the system. So that's really where MOSAIC is motivated, is to look at the processes, to look at the coupling in the system. So the overarching goal for MOSAIC then is to improve the understanding of that coupled system, the atmosphere, ice, ocean ecosystem, and the processes across those systems in the Central Arctic to ultimately support improvements in those variety of modeling perspectives. So from the science side, the key drivers for MOSAIC are listed here. The top level question, which has been developed over the course of many years through a number of different workshops, is what are the causes and consequences of an evolving and diminished Arctic sea ice cover? So it's a very broad question. Ultimately, it points to the central role that sea ice is playing and the interest that we have in understanding that change in the sea ice, both from the kind of forcing side, but also the implication side of that. But then MOSAIC is really organized around sub-questions that are related to that theme. Under these kind of, I listed four of them here that are are thematic areas of study, and generally those are focusing on the energy budget, energy processes, ice movement and deformation, some key atmospheric drivers, clouds, precipitation, and aerosols, and of course the biogeochemistry and ecosystems and how they relate to the changing system. So these are broadly the science drivers of MOSAIC, and of course each of these has a set of questions embedded within those, and of course a whole plan to go after those types of questions. There are also some important operational drivers for MOSAIC that have motivated us. One is an enhanced observing system. We recognize that observations are important across the Arctic, especially here in the Central Arctic Ocean. And in many cases, we don't have the capabilities to make the kind of measurements we need, especially in an autonomous fashion, which, in the long run, autonomous measurements are absolutely essential for understanding the Arctic and its transitions. And so MOSAIC is an opportunity to help advance some of those systems that are not yet ready for autonomous operations, such as surface energy flux stations being one key example there. Another key driver is interfacing with satellites. Again, MOSAIC is going to be a tremendous opportunity for satellites like ISAT-2 and many others to provide a constellation of measurements at the surface that will really be an unprecedented way to perform some ground validation and really enable the development of algorithms for using satellite measurements. From the data assimilation side, there have been a number of pilot studies over the last years to look at the impact, for example, of enhanced radio soundings in the Arctic Ocean. And MOSAIC provides this opportunity for year-round, 4 times daily soundings to really look at the kind of seasonal dependence and implications of additional sounding measurements in the Central Arctic on lower latitude and regional weather. Of course, multi-scale modeling and forecasting is very important. I'm not going to belabor that point much. You'll see some links to that through my slides here, but Wisla will speak a lot to those kind of implications. The concept of large-scale implications in general, right? The linkages question is a hot topic these days. A lot of people talking about it, and ultimately we have to ensure that the models we use can answer those kind of questions, especially with relation to surface energy fluxes, for example, that are ultimately tied into those processes. So we need to assess and ultimately improve our models so that we can answer questions like the large-scale connections of Arctic change with the global system. And lastly on this list, outreach and education. It's communication in many forms. How can we take this exciting work we do in the Arctic, and MOSAIC's a really nice opportunity to do that, to really link with a broader cross-section of society and to draw in more interested parties from the youngest ages on up to perhaps our parents at home that want to be educated about what's happening in the Arctic, and ultimately to draw in a new set of scientists for the future, the early career scientists that can really capitalize on this exciting opportunity to then go out into the community and push Arctic science forward. So those are some of the drivers of MOSAIC, but here's basically one slide summary of what we're actually going to do. So this is a year in the Arctic. So here we have a view of the Arctic, and we're going to install a ship in the Arctic. This is the Polar Stern from the Alfred Wegener Institute in Germany. And we're going to install that ship in the fall of 2019 at a point kind of like what we've put on this map here. And that ship is going to be the base of operations for intensive coupled system observations in the atmosphere, the ice, the ocean, the ecosystem, biogeochemistry. Around that ship will be a distributed network of observations installed, and these will be largely autonomous systems, providing some spatial context. Then over the course of the following year, that whole constellation will drift with the transpolar drift of the sea ice across the Central Arctic. So we'll have a full year in the ice, ending in fall of 2020. Along the course of that drift, there'll have to be some resupply efforts, and a lot of negotiations are underway to identify those ships and to ultimately get the fuel and the exchange of people that we need to support this drifting expedition. And over the course of the year, there'll be a few aircraft campaigns as well to provide some spatial context. So at its core, MOSAIC really has this multi-scale design, and this multi-scale part is really important for how the observations that are planned link in with the kind of bigger picture of Arctic research. So there's the central observatory. This is the ship. This is the people living on the ship and assets that are down on the ice near the ship. This is an opportunity for very intensive observations that really require people to be there. My own field of study is to use things like cloud radars to look at clouds, and we can't operate those autonomously yet. So we really need people to do that. Same with a lot of the biological activities in laboratories, et cetera. So the ship provides a stable opportunity to have people out there to really conduct some sophisticated measurements that help us to really understand key pieces of the system. And it's a stable platform to ensure that we get very solid measurements. Because ultimately this is going to be a huge effort that we really want to have a lasting legacy. And these kind of measurements at this very fine scale, a couple kilometers around a ship are very well positioned to feed into process modeling, high resolution modeling, large eddy simulation type modeling, etc. So a really nice link there. The next scale, if you will, is our distributed network. There's a little schematic off to the left with a bunch of little circles, and these would be different assets distributed around that central site of largely autonomous stations, so buoys, etc., some unmanned aircraft, unmanned vehicles in the ocean to provide the spatial context across a domain. You can see a scale bar there, multiple tens of kilometers. So this is kind of like a drifting grid cell, if you will, and this is something that I think is really exciting to the model community, because we're going to really attempt to quantify the variability of some of the key parameters across a domain that's relevant for representing models. So we see a nice link there. And then lastly, a large scale linkages scale. So this is getting to the Pan-Arctic scale. And it will largely coordinate the MOSAIC observations with other activities across the Arctic. There are a number of other ships that will be out there at different locations across the Arctic, including the ships that will come for resupply. A number of aircraft campaigns are planned already, and a number more are being discussed. So I think there'll be a lot of activity there. Of course, there are existing buoy networks across the Arctic, satellite observations. So a really nice way to link MOSAIC in with the broader Arctic observing suite, and to really help to upscale the observations from MOSAIC to those larger scales. So this is appropriate for linking in with large-scale models, etc. So as far as the kind of processes that we want to target with MOSAIC, this is a schematic that covers some of them, and it's not exhaustive, and I'm not really going to read through all of these. You can kind of see, the important pieces are this atmosphere, ice, ocean system, and how it interacts through energy, through physical processes, through the chemistry in the system, through the biology in the system, really cutting across this and really targeting some of the key drivers of variability in that system. So with that, I'm going to go into a few of the more specifics of some of the observations. Since this is the atmosphere team and the sea ice team coming together with the modeling team, I'll just highlight some of the specific observations that we have planned in the atmosphere and sea ice teams, so we can see in more detail what we'll obtain from MOSAIC. So from the atmosphere side, we'll have, I've kind of listed at the top there, a list of the kind of platforms, if you will, and then in the bullets, those are parameters. So we'll have radiosondes for a day. We'll have a suite of active and passive remote sensors for looking at the atmosphere. We'll have a meteorological tower. We'll have some in situ samplers. We'll have unmanned aircraft and a tethered balloon. And of course, there are the manned aircraft that I've talked about and satellites. So all these together will provide us this nice perspective on the following. Of course, the atmospheric state, moisture, temperature, winds in the vertical. Surface fluxes of radiation, turbulence, momentum, gases. A lot that you'd like to know about clouds: presence, macrophysical, microphysical properties, importantly phase, and some spatial distribution information. Precipitation is important, the precip rate, some spatial distribution information, how that links to snow depth, and using water isotopes to understand some of the trajectories that led to the water that we're seeing at the site. And in the aerosol and gas realm, radiative properties, size distribution information, activity with relation to clouds, and composition that might give us some information about the source of aerosol particles. Similarly, in the ice and snow observation realm, there will be a number of surveys, so manual surveys with humans, helicopter surveys, surveys with ROVs underneath the ice. There'll be a number of stations and buoys making continuous measurements, some coring and snow pit activities, radar and LiDAR for providing some spatial mapping, and of course, again, satellite measurements to really quantify ice and snow thickness, distribution, flow size distribution across our domain, to understand the topography of the top and the bottom surfaces. Optics of the ice are very important: spectral albedo, transmittance, etc. And of course, the physical properties of that ice are important: temperature, salinity, density, porosity. Snow on sea ice, the microstructure, density, temperature, snow water equivalent, and impurities like black carbon. Melt ponds are a critical element here, so understanding the geometry and their physical state properties, and the ice dynamics and mechanics, deformation, strain rates, ridging, and how that impacts size, the kind of ice thickness distribution. So those are a couple of the more specific measurements. A lot of these are I'd say already accounted for. We have a lot of these pieces covered by the various contributions so far. And so I think we're in really great shape to really manifest this full suite. There are similar lists for ocean parameters, for biogeochemistry, and for ecosystem that I'm not going to show here today, just based on the audience. But I do want to just provide a couple examples here of the kind of approach that we're trying to take, and how we combine the different measurements that I've listed there to look at specific aspects of the system in a coupled way. So here's a nice example. This is from Shupe. So this is back in the late 90s, and this is a couple weeks of data. And during this time period, this is January, so it's cold out. There's advection, long-range advection of moist air masses coming from Fram Strait all the way over to the Beaufort Sea area. In the top panel, what we see, can you all see my mouse there? Do you see that? Okay. So there's a couple pulses here in this top panel. It's a function of height versus time. These are measurements of clouds that are passing over a radar. So we see initially some kind of deep, almost storm systems, and then shallower clouds. The next panel down, we see in blue the ice water path, and in red the liquid water path. This is the total amount of condensed ice and liquid water. So we see ice, a little snow actually coming along with these kind of frontal systems, but then eventually we see these high liquid water path clouds. And these are at about minus 20 degrees. So this is super cool liquid water. These are classic Arctic mixed phase clouds. We see a big impact when this liquid water is there on the downwelling long wave radiation of 40 to 70 watts per meter squared, which has a dramatic impact on the net atmospheric energy flux to the sea ice. And then when we jump to the bottom, this is actually temperature profiles through the snow in the top layer and the ice and then down into the ocean. And we see actually pulses of energy, pulses of warmth going through that snow and ice when we have these liquid water clouds with their radiative effects. And that warming near the surface actually decreases the gradient of temperature through the ice, and it decreases the conductive heat flux. It's removing heat from the bottom of the ice. And ultimately what this does is slows down the ice growth rate. So we see this really nice coupling between large-scale advection in the atmosphere, cloud processes, radiation, surface energy budget, sea ice processes, and ultimately ice growth. So a very coupled system where we hope to understand how these pieces work together. There's a few other kind of conceptual things that we can do with MOSAIC, and I'm just going to lay a few of those out here. One is understanding closure. We talked about ice growth and the various fluxes that would impact that. So at a number of stations across the MOSAIC domain, we're going to measure ice thickness. We're going to measure the profiles of heat, tough temperature through the ice. And then we're going to have measurements of the fluxes from the atmosphere and from the ocean going into that ice pack. And so can we obtain closure over a full year of the energy that's transferred to and from the ice and the change in the ice itself? That's a really big challenge, and I think it's one that really is going to teach us a lot about what ultimately drives the annual evolution of the ice pack in a thermodynamic sense. But then you can imagine this spatial distribution of all the assets we have distributed along the ice. Something like these different colored dots here, these are different buoys. Every one of these will be measuring positions. So we can understand how the ice is deforming in time. So you can imagine having a certain area defined by these and trying to measure how that area changes, the ice thickness distribution in that, the energy fluxes in that, and somehow scale that accordingly to really start to get at closure in ice volume. That would be a huge challenge, and it's one that's going to really require bringing observations and models together. But again, I think it's going to really teach us a lot about how ice volume evolves over the course of a year. And then we can also think about momentum transfer, right? So each of these points will have some movement, and ultimately there'll be events where there's divergence in the ice or convergence in the ice that are really important processes for us. And we'll be measuring momentum fluxes between the ice and the atmosphere and the ocean at a variety of locations. And so can we gain some closure there in the momentum transfer? Another very interesting kind of coupled system is that between ice optics, light, and biology. So, of course, we'll try to sample what's happening at the top surface of the ice in terms of its interaction with radiation and how that ultimately affects the amount of light that gets down below the sea ice. And, of course, that then links into the biology in the sea ice and in the ocean which has links to the food web, but also to biogeochemistry and elemental cycles and nitrogen, carbon, sulfur cycles. And ultimately, those can link to things like gas fluxes to the atmosphere, which might feed back to aerosols. So again, here's a chain of many different links in a system of coupled processes that MOSAIC will really enable us to study. So just starting to wind up here a little bit, I want to make a couple points about MOSAIC in general. This is a very distinctive project. It fills some really important observing gaps, specifically looking at the coupled system. So many of our campaigns go out there and measure a very narrow disciplinary topic, but MOSAIC's really pulling together many pieces to look at the coupled system in an area of the Central Arctic that doesn't get a lot of attention in general in that regard. It's going to bring this year-round aspect, a full year, to look at continual change in the system, the evolving processes, interseasonal linkages, and to really get after, what happens in winter. There's a lot of questions about what happens in winter for a lot of parameters like aerosols in the atmosphere, like a lot of the biology. So there's some major drivers there that I think MOSAIC will be very distinctively able to address. And the heterogeneity component, right? Providing the spatial aspect, this distributed network, is something that the modeling community really wants. That's what we've really heard as we've designed this. And so that's another area that I think will be quite distinctive. So as far as the status, I just want to emphasize that, in quotes here, MOSAIC will happen. There's definitely some questions about that in the community, and obvious that Alfred Wegener Institute is very firmly committed to this. The German science minister came to the Arctic Science Ministerial last September and committed this as an activity that Germany was contributing to the Arctic community, and AVI is very much beholden to their science minister. They are going to stand up to this commitment. And so in recent times, they've been negotiating agreements with Russia and with China for support, icebreaker support in particular, to support the resupply. This is an area where the U.S. can, and I believe should, be involved as well. The Healy is very capable and actually is very eager, in talking to a number of the Healy personnel, to play a role here. And so this is something that I think that, we as a community can push forward. As far as specific U.S. contributions, I've listed some of the relevant agencies here. DOE has committed an atmospheric mobile facility, which is providing a ton of the atmospheric measurements that are needed for this project, and really is a nice nucleus to build a lot of the other contributions around. NSF is currently making decisions about a number of proposals. I think there's about maybe 12 proposals submitted already, and perhaps a few others that are going to be coming on in the near term here. And those proposals are coming from a rock star team of different scientists. These are all-stars from the U.S. community, and it's really a diverse collection of science that's represented in those that really nicely plugs into the overall MOSAIC mission and design. NOAA is on board to support some operational sea ice forecast modeling and some instrument development. There's also opportunities to link with ONR. A few recent DRIs, polar cyclones, autonomous observations provide, I think, opportunities for links there that can really be pursued. And there's opportunities with NASA as well. Of course, the ground validation aspect is drifting constellation of measurements for linking with ISAT-2 and other satellites. And there's discussions about potential NASA-based aircraft campaign. In the international community, there's a lot more activity. And what we're seeing now, I think, is that, now that this ship is sailing, and that there's some certainty with that, we're starting to see all kinds of people really engage and really want to get on board. And I think, ultimately it's quite exciting to see this process unfold. My last real slide here is I just wanted to point to IARPIC goals. I think MOSAIC serves a lot of what IARPIC has laid out in its plan. It speaks to 19 different performance elements that are laid out, and I've listed those here. So MOSAIC is really well positioned to serve a lot of what we being IARPIC have decided are our priorities. And I look forward to, and I know the rest of the MOSAIC team looks forward to working with the U.S. community to really manifest this and to really utilize MOSAIC to best serve these kind of purposes. So with that, I want to say thank you, and I really would just want to emphasize that the U.S. has played a major role in MOSAIC from the beginning in terms of science leadership and design leadership, and they can continue to play this major role going forward. I think we bring a lot to the table. We have a lot of expertise. And we have certainly a lot of interest in the results of MOSAIC. But we ultimately need active engagement and coordination, and that's where I think IARPIC can play an important role in that. I welcome you all to look at science and implementation plans at the webpage, and happy to take any questions. Thanks.
Thanks very much, Matt. Do we have any questions from the audience for Matt before we move on to Wisław's talk? All right, I'm not hearing any specific questions now. I think what we'll do is move on to the next talk, and then we may have a little bit of discussion after both of our talks are done.
So Wisław, you'll want to go to share screen now.
Can you hear me?
We can hear you. We're looking at your desktop, it looks like.
Yeah, it should show the first slide of my presentation. No?
Not yet. Maybe you need to click on the PowerPoint.
I already did. I'm showing that I'm sharing my desktop. The only option I have is stop sharing the desktop.
So on your desktop, are you seeing the Maslowski MOSAIC PPTX? Can you double click that?
Hold on just a second.
I think the trick is to choose the right window when you start sharing. I fell into that trap myself.
Let me stop sharing and try again.
So if you share your desktop, and then you can, when you get in, then you can go to the PowerPoint.
Can you see my background?
Yep.
And the IRPIC folder?
Yes.
How about now?
Now it's working. Yep. And you can go to full screen. Yep.
Okay.
Okay.
Is this working okay?
Yes, looks great. Go ahead.
Okay. Thank you very much, Alice, and the other leads on the IRPIC, several working teams. I'm representing here some results and some plans for modeling activity associated with MOSAIC, with contributions from Annette Rinkek, who is co-lead at Alfred Wegener Institute on the modeling side with me. And then we also have contributions from John Cassano at the University of Colorado in Boulder, Klaus Detloff at AVI, as well as two teams from Cordex, the atmospheric model comparison, comparison, mostly focused on atmospheric side, and also regional Arctic system modeling team. What I like to talk about, okay, switch my slide. Maybe here. Okay. I want to start where actually Matt Shupe has ended up in his conclusions, basically looking at generally at the recently published U.S. Arctic research plan for 2017-2021. There was 9 goals, and I'm listing here 4 of them, which I believe are highly related to what MOSAIC plans to do, both on the observational side and the modeling side. I'm not going to read those, but they basically cover the atmospheric composition dynamics, understanding of the changes and prediction of the sea ice cover, understanding of the structure and function of ecosystems, and basically the overall enhancement of frameworks for environmental intelligence gathering, the new collaborative team that has been formed with this recently published plan. Also, I wanted to mention that from the DoD, and in particular from the Navy point of view, the Arctic Roadmap, published a couple of years ago, has a very explicit statement saying that one of the tasks for the Navy is to, and DoD in general, is to encourage research into and development of comprehensive Arctic system models. And those models require observations, understanding of the system and process level and feedbacks in the Arctic to improve their representation in the Arctic. And actually our research on the regional Arctic system modeling, one of the key hypotheses is that representing mesoscale processes and resulting feedbacks should improve the representation of the state of the Arctic climate system and also prediction of polar amplification and global climate change. So I believe that MOSAIC is actually well positioned into this. And one of the key uncertainty, or actually very limiting factor in the Arctic system modeling, that if you look at the slide I'm showing here, schematic, based on work from Mark Ceres, 2007, with some additional caveats, and eventually maybe different people might have a different perspective, but the bottom line is that the radiative budget, or the energy budget in the Arctic, doesn't balance out. We have residual of order of tens of watts per square meter, especially in the winter, that we still need to reduce and hope to make it available for constraining fully coupled regional and global climate models for the Arctic region. Also, the other thing is that we're dealing with a very complex environment in the Arctic, and Matt already alluded to this in terms of the sea ice cover presence between the atmosphere and ocean, in terms of different timescales. For example, when you have open water in the winter, you have convection associated with the leads, which can be on different spatial timescales ranging from 10 meters to 10 kilometers or so. We have also, cold air outbreaks at 100 kilometers, marginalized zone of order of 100 meters to kilometers. And we're dealing with melt ponds, which are order of tens meters in the Arctic ice pack. Then we have convection over leads, which can be 10 meters to 10 kilometers. And then we're dealing also with pressure ridges, which could be order of 100 meters across, and 1 meter or so high, but they could be actually very long features in the spatial scales in a plane view. So sea ice morphology affects the heat and moisture fluxes, radiative fluxes, momentum flux, atmospheric convection process, and so forth, which in general basically has a very large impact on the atmospheric boundary layer, the sea ice surface conditions, and then their impact on the air-ice-ocean interaction. So another thing that Matthew has already alluded to is that transfer of the momentum from the atmosphere through the sea ice into the ocean. And there's some studies, in particular, we're mentioning here, Pierre Rampal from 2009, which basically diagnosed that without much of the changes in the atmospheric conditions in terms of the oceanic atmospheric winds, the ice has been drifting much faster due to thinning of the ice. And then by thinning of the ice and moving ice faster, we have much more momentum transfer into the ocean related to oceanic mixing and the potential entrainment of heat from layers below, if there is heat available below the mixed layer, especially in the winter. So in terms of the participation and interest in the MOSAIC, there's a large group of people, or multiple teams of people associated with the Arctic Codex. There's a list of 13 participants related to Arctic Codex, which is mostly focused on the atmosphere, but also there's interest in the expanding those efforts into the fully coupled model configuration. And their circumarctic domain covers the region that is shown on the left here, Central Arctic, and communication to the subpolar Pacific and subpolar Atlantic, with different resolutions ranging from roughly about half a degree to 1/6 or 1/7 of a degree. And you can see different groups participating here on the right, with already ongoing activities, and they expect to be heavily interested in the Arctic measurements from the MOSAIC field experiment, and hopefully benefiting from model improvement, evaluation, and then providing also some contribution back to the MOSAIC. As far as our regional Arctic system model, which is more closer to what I understand much better, we're looking in the fully coupled regional model, which is forced by external boundary conditions along the lateral boundaries, also at the top, from reanalysis or global climate models. And we have atmospheric components, we have the land component, the ocean component, sea ice. They're all connected through the flux coupler. We're also looking into already expanded actually, the marine biogeochemistry, both on the sea ice side and the ocean side. And our model configuration default is at 50 kilometers for land and ocean and sea ice, land and atmosphere, 9 kilometers for the ocean and sea ice. We have recently been configuring the ocean and sea ice at about 2.4 kilometers, and the atmosphere is proceeding to new configuration at 25 kilometers. At that different level of detail and resolution, we're strongly interested in understanding processes, evaluating their representation in the regional models like RASM, but also the standalone or more force models like atmospheric models with boundary conditions at the surface, or ice ocean simulations with prescribed atmospheric forcing. So I'm showing here previous results that when we do realistic forcing with reanalysis such as Core 2, we can quite well represent the pan-Arctic distribution of winter or summer ice conditions back in the climatological area such as 1995, for example. The upper left panel showing the March ice thickness distribution, and there's a green contour here shown on both sides of the Atlantic and Pacific subarctic, which is the actual passive microwave estimates of the ice extent for that particular month and that particular year. Then you move to 1995 for September. You can see the model representation of the ice extent, but the shading actually is representing the ice thickness distribution. Now on the right panels are showing the 2007 winter with the same comparison of the passive microwave with the green contour, and then September of 2007. So this is just basically to show that models like RASM, they increase and show quite a promise in terms of representing the sea ice cover, both at the seasonal variability as well as interannual and multi-decadal variability. More recently, for the SIPIN contribution this early June 2017, where we predicted the 2017 September minimum, we have run fully coupled model simulations with upgraded model components in RASM. In particular, the WRF has been upgraded, and there has been some improvements in the sea ice. And those three panels that I'm showing here are representing the actually results from the fully coupled RASM simulations, with the purple contour now representing the 15% satellite observational estimates of ice extent, and the end of the shading with the black contour here representing the model estimate, fully coupled model estimate of 2007, the middle panel for 2012, and now the 2016. We didn't have the passive microwave observations. I'm showing the panel below with the white shading to compare with the black contour line for the 2016, which were actually used to, as initial conditions, fully coupled regional climate model initial conditions to contribute to initialize model simulations, sample member simulations for September 2017 prediction. So the bottom line is that the models have skill, they represent different processes. One of the processes shown here is the inertial oscillations that we can resolve in the RASM, and they can also be resolved in coupled climate models like CSM if the coupling frequency is increased to appropriately to resolve them. And basically you can see that the model comparison in the red line and the green line observations from buoy represents the inertial frequency quite well, shown on the upper panels. And when we have not enough frequency for coupling frequency in the coupled climate model in the bottom panels, you can clearly see that the inertial frequency will not be resolved. But the bottom line, one of the processes, inertial frequency, which has to do with the ice deformations, which is shown now in this panel. And I'm showing a sequence of evolution of the ice divergence in the top panels, and the fragile ice representative or respective fragile ice growth formation represented with those linear kinematic features developed in response to the passing of the synoptic storm in the Western Arctic. You can clearly see that the fragile ice in the bottom panels shows up as the growth along the lines where we have deformations, positive divergence in those leads that open with the passing of the storms. As the storm passes over a week time period between, say, January 20 here and January 26th of the 1980, we produce new ice, and this ice contributes to the ice thickness distribution and variability in the ice overall volume and seasonal and interannual variability. This panel shows here the representation of the total ice volume in the fully coupled model and the force simulation when we use different rheology. One of them is the earlier one being the elastic viscoplastic, and the newer one being the elastic anisotropic plastic. Clearly, the anisotropic rheology, which is shown here in black in the top panel, shows more deformations and more volume related to those deformations compared to the EVP volume shown here in the green color. And then the other aspect is that when you run a fully coupled model comparison, regional model comparison rheology, we have a change in volume order of 20% when we have force simulations with prescribed reanalysis for the atmospheric forcing. We only show roughly of the half of the increase in the ice volume related to the rheology. So the importance here is that running fully coupled models actually is quite clearly represented with this example, where we basically have increase of double, factor of 2 increase in the total ice volume related to different rheology and more realistic representation of the ice deformation with the anisotropic rheology. The next thing I wanted to show is that in terms of the air-sea fluxes in the winter in the Arctic, the upper left panel is showing that in the Western Arctic, due to the deformations commonly occurring along the border between the fast ice and the pack ice here, shown in green, we can have order of 20 to 50, 30 to 50 watts per square meter in a monthly mean during the winter time of heat released through those leads into the atmosphere through gaps in the sea ice. And then in summer, we have order of 250 watts per square meter. In the Western Arctic now, we go to the Eastern Arctic, to the Nordic Seas and the Barents Sea. The heat flux is associated with the marginal ice zone and the ice edge position, shown here by some of the blue colors here, can be in excess of 350 watts per square meter. So this is not necessarily associated with the mosaic drift, but the question is that if we can measure the heat fluxes over the lead during the drift of the mosaic from the nearby locations, this would be very important information for constraining model representation of those air-sea fluxes, especially during the winter time, and somehow validating more model representation of those air-sea interactions. Another aspect is, of course, the freshwater content. And again, we likely will be drifting along the edge of the maximum freshwater content that is shown here from observations in the left panels. But I'm showing that the models such as RASM can represent the variability in the recent time and the interdecadal variability in terms of increased freshwater content in the Western Arctic associated with the ice melt and increased hydrological cycle. So observations along the mosaic drift would actually be very helpful in terms of understanding how far this excess of the freshwater content that we have recently observed and simulated is reaching out to the Central Arctic and also might be to the Eastern Arctic. From the ocean point of view, it's important to possibly try to find, measure, diagnose eddies from observations that would be very useful in terms of providing information to the models for evaluation, for comparison of the eddy kinetic energy estimates and so forth. But also from the process point of view, those eddies might be important in terms of entraining water from the below mixed layer into the mixed layer. And if we happen to have some warmer water below the mixed layer, that might be actually a very important aspect of forcing the bottom of the sea ice in terms of reducing the ice growth through the winter or increasing or accelerating melt during the spring and summertime. So I'm kind of trying to wrap up. The bottom line is that advancing Arctic climate model capability and predictive model capability requires understanding of the processes that might be critical in the Arctic system, in the operation of the Arctic system, and their representation in the model. So basically coming up with understanding and then somehow translating that understanding into improving the models. If we improve the representation of processes, we will definitely improve the representation of the coupling along different channels between the atmosphere, sea ice, ocean, land, and biogeochemistry. And then we can also look at the sensitivity if we understand the processes and have some estimates of measurements, for example, such as air-sea fluxes in the winter or the eddy kinetic energy in the ocean. We can look at the model representation of those processes as a subject of sensitivity to a parameter space. And in addition, different models are force models, such as atmospheric models with prescribed boundary conditions, or the ice ocean models forced with reanalysis, as well as regional models. They're part of hierarchy in modeling that will be useful in terms of reducing uncertainty and improving prediction at different timescales, starting from subseasonal to seasonal and into decadal prediction. So I'm probably running out of time. So I just want to talk about how our regional climate model can benefit from MOSAIC. Basically, again, repeating what I already said, is that my understanding and measurements of processes can be used to derive the improved representation of the processes in the climate model, regional climate models. And then we can run those regional climate models to compare them in terms of fully coupled simulations, how they represent not only processes, but also the feedbacks. Finally, our regional climate model simulation strategy for MOSAIC. There are plans for running models at different spatial resolution, ranging from few kilometers to tens of kilometers. And we're talking about not just one simulation or two, but ensemble simulation by different group participating in the projects like Arctic Cortex, for example, or RASM. Using force simulations with ERA interim or JRI 55 with prescribed boundary conditions for atmospheric models or regional atmospheric reanalysis for the ice ocean simulations. The plan is to actually have very high temporal output from those simulations to compare to the details of observations that will be coming from MOSAIC. And in addition, those simulations will provide high spatial resolution, realistic boundary forcing, high temporal output, constraint and free runs. There will be a series of process studies associated with the MOSAIC observations that somehow different groups will contribute and possibly translate into model parameterizations that can be then implemented in the regional model and global climate models and run in an ensemble approach for different model simulations and different objectives from the scientific point of view. Atmospheric key processes and their evaluation, in particular what Matt already mentioned. The issue here is that sea ice surface and their interactions with the atmosphere above and also the ocean below is related to leads, the snow cover, melt ponds, and overall albedo of the surface of the snow and ice. Already mentioned radiative and turbulent heat fluxes, moisture and momentum fluxes, which is critical in terms of representing the fully coupled model representation. So thinking about the MOSAIC measuring a fully single column information and providing that for model evaluation at different model component level and also in a fully coupled system. I cannot overemphasize the importance of the cloud microphysics in terms of the energy exchange through the sea ice into the ocean and back to the atmosphere, and also the importance of the vertical atmospheric structure in terms of how those fluxes are communicated into the sea ice and then into the ocean. Matt already mentioned the implementation plan. There's also a MOSAIC science plan that is listed here on the bottom. And I think that I'm running out of time, so probably that's my last slide. Thank you very much.
Okay, that was great. Thank you, Lisa. Do we have any direct questions for that presentation? Well, I had just a comment I wanted to make. First, Matt, I wanted to thank you for going through the research plan and picking out those performance elements that were relevant. And I just wanted to mention that we wrote this plan and these performance elements for a 5-year period, but it's really kind of a starting point. And I just want to remind everybody that those performance elements are somewhat fungible. We can work with those as we go to really direct them towards the questions that we think are most pertinent and relevant. And so I just wanted to say in relation to things like the huge importance of understanding these coupling channels in the models and using the model hierarchies, that reflects a little bit of the research objectives I think that we have written into our research plan in bringing observations at different spatial scales together. So I would just say to the MOSAIC team to use us as a forum use IARPIC collaborations as a classified section for pushing those efforts forward and getting what you need out of this community.
Yeah, thanks for that, Allison. I think that, as we're moving forward and gaining more kind of solid commitments from U.S. funding agencies, I think that helps to enable the process. And so, I believe, like you said, that there's a lot of opportunities for linking with the IARPA plan, and to the extent possible, as there are, ways to evolve some of the goals. I think that we have an opportunity to do that, to really, specifically harness some of these details and ultimately to guide some of them as well. I think that, MOSAIC can provide a lot, and we do have an ability to target that in certain ways. So I think it's important to have that dialogue.
Great. Do we have any other comments from CICE or modeling, or any other questions from the general audience?
Yeah, so this is Hailong Wang. I have a question for Matt about you said a year of measurements. Is that just including the fixed ship at that certain location and the drifting?
Yes, for the drift will be about a year. That's the goal.
Mm-hmm. So the measurements, it's hard to get like a long kind of at least a month of measurements at a certain location, except for the first period of the fix the ship at that certain location. When it starts to drift, you have like kind of pretty short-term measurements. So my point is that I'm doing mostly interested in aerosols in global models. So I'm more interested in the seasonal cycle of, for example, aerosols and like black carbon in snow. So those are very important measurements to evaluate model. So I'm thinking if there's any longer seasonal measurements for that purpose.
Well, at the ship, those kinds of measurements will be made for the full year. So we'll get a full year of that. Now, in terms of longer term than that, this is one of the major gaps that we have, and part of the motivation for why we've pushed forward for MOSAIC is to at least get 1 year. But for many of the questions that you have right there that you raised, we have very few observations over long time periods. So those are things that, might motivate future missions, but hopefully, we'll get a nice perspective from this year-long observations from MOSAIC.
But also, further question is that there are a couple of fixed sites. Are you going to coordinate with those sites? For example, also measure black carbon in snow at those sites, near the sites?
I personally am going to try not to oversee too much of that, but certainly we are coordinating with many networks. And so we appreciate and acknowledge the value of some of the long-term observatories that are on the coastal areas of the Arctic. And certainly we're coordinating with those sites to the extent possible. A lot of those, might be the mechanism to get long-term measurements. The extent to which they represent what's happening out over the ocean, that's another question. But yeah, certainly we will attempt to coordinate to the degree possible.
All right, thank you.
Okay, we have a few minutes left. I would like to move on just to the last agenda item, which is member updates, if we don't have any further questions. And of course, if you do, contact our speakers directly or through the IARPIC website later. Thank you both, Matt and Wisla, for providing that overview for us, and I hope that we'll continue these discussions on MOSAIC. A couple of announcements that I did want to make before we sign off are on a couple of relevant efforts that are going on out there. One is actually external to IARPIC, but have asked the IARPIC community for input. And that is excuse me, trying to find my right web pages here. So Sarah has displayed for us a post on the IARPIC Collaborations website, and you can find that there yourself. This is in reference to a special issue of the journal Climatic Change, and this is going to feature 15 different indicator papers, and one of these papers is specific to the Arctic. And so the lead author on that Arctic Indicators paper, Diane Stanitsky, has reached out to the IARPIC community to please provide input on what these most important indicators will be. And I don't want to spend too much time on this because information is here on the website. But if you have ideas about existing indicators or things that could be developed to indicators, they would be very grateful to get your input. You can leave comments here at the bottom of this post as Sarah is showing us, and they will integrate all of this information and communicate with you about those indicators and how they might be ranked and included into this journal issue. And then one other thing that I wanted to mention is that the Environmental Intelligence team, which houses the modeling collaboration team within IARPIC that is meeting with us today, has developed a cross-cut activity that's focused on the carbon cycle. And this is a graphical representation of how this cross-cut effort is working. Basically, the Environmental Intelligence team has its own cycle for how it works. And this includes decision support, leveraging data archives, filling observational gaps, integrated system level modeling, analysis, and assessment. And of course, all of these things feed right back into decision support application. As a matter of fact, there was a lot of discussion about where to start this cycle and what to put at top. But as a kind of example end-to-end effort in environmental intelligence in the Arctic, this team has decided to focus to start with on a carbon cycle effort. And so the carbon cycle is mapped onto this environmental intelligence cycle. And I just wanted to bring this to everybody's attention. We're starting to talk about how the different teams can contribute to this effort, or conversely, how they can benefit by developing existing performance elements or even building on new ones that are relevant to this effort. So I wanted to bring that to everybody's attention, and there is a workshop to discuss this. Sarah, can you fill in any details there, or is Emily available to do that?
I got it. It's July 31st. And webinar workshop open to anybody. And I will see if I can pull it up here. And you can register to attend. We'll have it webcasted and everybody will be invited to attend. Here it is. It's a forum from 2:30 to 4:30 on July 31st. This is Eastern time.
Great. So I think you can see that with this new plan, IARPIC is very interested in integrating. And again, I think MOSAIC is just the perfect platform for being able to do that. So I wanted to thank again our speakers, and please contact them or interact with the whole team or each of the 3 teams on IARPIC collaborations. So thanks everybody for joining us. And I think with that, we're 2 minutes over our time and we shall sign off.
Thank you.
Thank you, Allison. And please keep the dialogue going on the website. Use the comment boxes at the bottom of the pages to continue the dialogue.